So any coil, if a current passes through it, it will have a magnetic flux passing through it. So any coil can be called as an inductor. Even a single loop, single conducting loop, you can call it as an inductor, or a spring-like coil. The shape could be anything. It can be a square coil also, doesn't matter. You can call such coils as inductors. Fine. The circuit symbol for an inductor is this, just a spring. Okay. Now, how many turns you keep is your choice. Fine. Let me draw it neatly. Right. So this symbol represents an inductor, basically a coil. Okay. Now, what happens when current passes through the coil? A magnetic field gets set up and the magnetic field produces flux. Okay. Now consider something like this. Let's say there is this coil in a circuit. Let's understand what an inductor does to a circuit. Assume there's a switch which is initially open, a battery, and some resistance in the coil, in the circuit. Okay. Initially, the switch is open. Tell me, when the switch is open, will there be any current in this circuit? Current needs a closed path to flow. So there won't be any current when the switch is open. If there's no current, the magnetic field in the inductor is 0. And the magnetic flux in the inductor is also 0. There's no flux. Okay. One of you tell me, what will happen the moment we close this switch?
Sir, there will be a magnetic field produced.
Okay. So the battery will create a potential difference. It will start driving current. And when current passes through the coil, a magnetic field gets produced. Correct. Earlier, there was no magnetic field, there was no flux. Now suddenly, the moment you close the switch, a magnetic field gets generated, flux gets generated. So magnetic field in the inductor becomes non-zero. Magnetic flux also becomes non-zero. Now see, earlier when the switch was open, the flux was 0. When the switch is closed, the flux becomes non-zero, means the flux changes. Okay, flux in that inductor changes. Now you all tell me, when flux through a coil changes, what happens? When flux through a coil changes, what happens generally?
Sir, will an induced EMF be produced?
Correct. Okay, an induced EMF gets generated. And what is the tendency of this induced EMF? What does it tend to do? Does it support the change in flux or does it oppose the change in flux?
Sir, its induced EMF is inversely proportional, so it does not.
Inversely proportional to what? Where are you bringing this from?
No, like, I mean, like,
Huh?
I don't know how to explain it, but like,
Okay, induced EMF is inversely proportional to what?
no, I mean to say as that, like, the more flux there is, the lesser induced EMF is there.
There is no law like that. Where did you learn that?
No, I'm just, uh, like,
No, there is no such thing that greater the amount of flux, lesser the induced EMF. No,
no, I was just assuming something like that. So,
no, you should not assume. No. Okay, tell me Faraday's law, Rishi.
sir, Faraday's law is like
Okay,
it's uh,
tell.
it's flux by time.
What is flux by time?
Uh,
Okay, Isha, can you tell Faraday's law? Statement or the formula at least.
Uh, Sir, when the magnetic flux is linked to a coil, then the induced EMF is produced in the coil when the flux changes.
When flux changes, induced
And
EMF is produced. Continue.
it produces as long as the flux is produced.
No, you are
And
saying
it
as
opposes.
no, that opposition and all is Lenz's law. But Faraday's law itself, you are saying as if there will be an EMF as long as there is flux. No. See, flux must change.
Change,
That is
yes,
when
sir.
EMF gets produced. And the induced EMF is proportional to rate of change of magnetic flux. Okay, don't create your own laws. Scientists have done the experiments and found out the behavior of like devices. So this is what is Faraday's law. EMF induced in a coil is proportional to rate of change of flux. Faster the change in flux, greater the EMF. There is no inverse proportionality anywhere. Okay. Faster the change in flux, greater the EMF produced. If flux increases rapidly, more EMF will be produced. If flux decreases rapidly, also more EMF will be produced. Okay. And then comes Lenz's law. Yeah, Isha, tell me, what is the direction of induced EMF or what does it tend to do?
It opposes the
Huh.
magnetic flux.
No, it doesn't have to oppose the flux. It has to oppose the change in
Current.
flux.
Okay, yeah, change in flux.
Huh. If flux is increasing, then induced EMF will create a field opposite to it. If flux is decreasing, if the existing flux in the coil is decreasing, then induced EMF produces magnetic field in the same direction to support it. Okay, keep these points in mind. Anyway, fine, I'll give you some more problems, practice problems based on this. Okay, now observe what happened here. There is a coil connected to this circuit. When the switch was open, there was no current, no magnetic field, no flux in the coil. The moment the switch is closed, current starts to flow, a magnetic field gets produced in the coil, a flux gets generated through the coil. So zero flux became non-zero, means flux is increasing. It's changing, it is increasing. Zero became non-zero. Then there will be an EMF induced. Okay, definitely it will be there. And what does induced EMF tend to do? It tends to oppose the change in flux. Now, what happened to the flux here the moment we close the switch? Flux increased. Okay, from zero it became non-zero, it increased. Then what the induced EMF will do is it will try to decrease the flux. Now, why did flux increase? Because current went from zero to non-zero. Current increased, that's why flux increased. Okay, current increased, that's why the flux in the coil increased. Now, induced EMF will have to oppose the change in flux, means it will have to decrease the flux. How can it do that? It will have to decrease the current. So what will happen is the moment you close the switch, there will be a EMF generated across the ends of the inductor. Means there you will see an EMF between these 2 points and that EMF will oppose the current. Now what is this main battery trying to do? This main battery is trying to drive the current this way. Then the EMF induced in the inductor. Okay, this current is increasing, no? From zero it is becoming non-zero, means this current is increasing. Then the induced EMF will try to oppose it. So induced EMF in the inductor will be like this. It will try to drive current in the opposite direction and reduce the current, reduce the change in flux. Okay. So if current in an inductor is increasing, induced EMF will oppose the current. Why? Because if current is increasing, it means the flux is increasing. And induced EMF always tends to oppose the change in flux. If flux is increasing, the induced EMF has to decrease the flux. So the induced EMF will get generated in such a way that it decreases the current. Okay, so it gets generated opposite to the current if current is increasing. Now consider another situation. Or okay, let us discuss this itself a little bit more. The current was initially 0. The moment you close the switch, the current starts to increase. Okay, it becomes non-zero. Now, one of you tell me, what is the total resistance of this loop? How much is the total resistance in that loop?
R.
R. Okay, and the battery's EMF is E. Now, generally, when a resistance R is connected across a battery of EMF E, how much current should flow in this circuit? I is equal to E by R, Ohm's law. That much current should flow. So in this inductor loop also, we expect the current to be I is equal to E by R. When the switch was open, there is no current. When the switch is closed, we expect it to become I is equal to E by R. But the current won't increase suddenly to E by R. Why? Because when the current is increasing, the induced EMF opposes the current. So it won't allow the current to become E by R. It will take some time to attain that value. So what is the inductor effectively doing here? It is preventing a sudden increase in current. Okay. If it was a simple circuit like this, only a battery and a resistor. Assume the battery is not connected yet. Then here in this case, the current would be 0. The moment you close the switch, the current becomes E by R. Okay, it will suddenly increase to E by R. But if you put an inductor in that loop, inductor is a coil, right? So current, the moment you close the switch, current tends to increase. Zero current becomes non-zero current. So current tends to increase. Then flux in the coil tends to increase. If flux in the coil tends to increase, then the induced EMF will oppose it. So what should it do? Induced EMF should try to decrease the current. So it will get induced in a way that it opposes the current, as you see in this diagram. So if current is increasing, induced EMF is opposite to the current. Okay, let's consider another case now. Suppose the switch was initially closed and some current was flowing in this circuit. Okay, let's say some current I was flowing already. Now you open the switch. Here the current is non-zero. If you open the switch now, suddenly, tell me what happens to the current when you open the switch. It tends to become zero, right? You are not giving a path for the current to flow. Current tends to become zero when you open the switch. So from non-zero, it tends to become zero, means current is decreasing. If current decreases, magnetic field decreases, magnetic flux decreases. Now see, which way was the current flowing initially? Current was flowing clockwise, means it was flowing this way. Current. So flowing to the right. And what is happening to that current? You're about to open the switch. Current is about to decrease. If current decreases, flux decreases. Then what will the induced EMF try to do? It will support the flux. Okay. If flux is increasing, it will oppose it. If flux is decreasing, it will support it. Okay. Because ultimately it has to oppose the change. Okay. So here what is happening? The flux tends to decrease. Then the induced EMF should support it. Means it should support this current. So in this case, the induced EMF will be in the same direction as current. It will try to produce more current in this direction. So you'll see positive on this side and negative on this side. So, okay, we'll discuss this in detail later. Basically, what an inductor does is it prevents the sudden changes in current. If current has a sudden tendency to increase, the induced EMF in the inductor will oppose the current. It won't allow it to increase that fast. And when current has a tendency to decrease also, okay, the induced EMF will support the current. It won't allow it to decrease that fast. It won't allow it to decrease suddenly. Okay, so if you have an inductor in a circuit, you can prevent sudden changes in current. That is what effectively an inductor does. Okay. Just a moment. Yeah, you can consider this coil as an inductor. Okay. Let us derive an expression for the induced EMF in an inductor. Suppose this was the wire and an inductor is placed. According to Faraday's law, we know EMF induced is d phi by dt. This gives the magnitude. Fine. The actual formula is minus d phi by dt. Let it be. It depends on the rate of change of magnetic flux. Okay. Now, for an inductor or for a coil, generally for any coil, we know self-inductance is the magnetic flux divided by its current. Therefore, flux in the coil will be Li. Therefore, the magnitude of EMF induced will be d phi by dt, rate of change of magnetic flux. That will be the derivative of Li. Okay. L is inductance. You know, inductance depends on medium and geometry. So it's not something which changes with time. Okay. So L is constant. Put it outside the integral. You get this as L di by dt. That's the magnitude of EMF. Okay. Did you all understand this? Di by dt is rate of change of current. So depending on how rapidly the current through the inductor is changing, an EMF will get induced in it. If current in the inductor doesn't tend to change at all, then the magnetic field won't change, the magnetic flux won't change, there won't be induced EMF. Okay, only when current tends to change, there will be an EMF induced. Okay, now listen, suppose current is flowing this way. Current is flowing to the right. Let's consider 2 points on this coil. Call this end as X, call the other end of the coil as Y. Okay, we have to find out what is the EMF between X and Y. We got the magnitude L di by dt. We should find out which side will be at higher potential compared to the other side. Okay, magnitude is L di by dt itself. Okay. Now you all tell me, first case, if current increases, what will the induced EMF try to do? Will it increase the current further or will it try to oppose the current? If current in an inductor is increasing, what will the induced EMF try to do?
Oppose the current.
Oppose the current, because if current is increasing, flux will be increasing. Induced EMF will have to decrease the flux, so it will have to decrease the current. Now to oppose this current, I'll give you 2 options. Which way should the EMF be induced? Like this or like this? First way, first option or second option? Okay. Let's look at a simple circuit. Suppose there's a battery, resistance. You know there will be current flowing in it if the circuit is closed. current will be flowing this way. Okay. Suppose you have the option of introducing an extra battery here and you want to decrease this current. Okay. If you want to decrease the current, will you introduce the extra battery with this polarity, positive to the left and negative to the right, or with this polarity, negative to the left and positive to the right? In which case, first case or second, will the current decrease or will the current be lesser? Okay, let me draw both the circuits at least. That way I think it will be better. So one option is positive to the left, negative to the right. Another option is negative to the left and positive to the right. Just tell me in which circuit the current will be more. Is I1 more or I2 more?
Sir, I2.
What did you say?
I2.
Okay, why will I2 be more than I1?
Sir, because it's normally supposed in like
What happened? You got muted.
sir, it's because in normal circuits, if we look at them, they're like opposites are like together. So and
Okay, okay, fine. So they're connected in series with the same polarity. Listen, the battery of EMF E, okay, it tends to drive current this way. The other battery also tends to drive current in the same way. Okay, so it's like their EMFs will add up. Okay, both of them will produce current in the same direction. Okay, whereas in this case, in the first case, if you see, one battery is trying to drive current this way, the other battery is trying to drive current in the opposite direction. So effective EMF here will be E minus E dash. And in the second case will be E plus E dash. So you'll get more current here. Okay, if the batteries are supporting each other, if they're connected with the same polarity, then you'll get more current. Now you tell me, I told you that the current in this inductor is increasing. Somehow it is increasing. Due to some external agent, the current in this inductor is increasing. You know induced EMF will have to oppose this current. So tell me how the induced EMF, tell me what the polarity of the induced EMF will be. Will it be case 1 or case 2?
sir, case one.
Case 1. Okay. It will have to oppose the current. If current is increasing, it will have to oppose. So if current is increasing, case 1 means X is at higher potential, Y is at lower potential. So potential at X will be greater than potential at Y if current is increasing. Okay, Pradyun, is this clear? Okay, you can ask if you have any questions. So I hope you all understood. If current in the inductor is increasing, this is what will happen. Let's consider another situation now. Let's say current is flowing to the right itself, but the current is decreasing. Okay, second case. Just a moment. Second case, if the current is decreasing, tell me what should the induced EMF do? Should it support the current or should it oppose the current? By some means the current is automatically decreasing. So what does the induced EMF do now? Will it support the current or will it oppose the current?
Support the current.
It has to support. Then tell me with which polarity, with what polarity should the induced EMF get produced? 1 or 2 to support the current?
Sir, 2.
Case 2. Okay. That means potential at X will be less than potential at Y if the current in the inductor is decreasing. Okay. Now we know magnitude of EMF induced is L di by dt. And also, this is also quite tricky actually. If current is increasing, di by dt is positive. If current is decreasing, di by dt is negative. So we have to put a modulus here for magnitude. But anyway, we'll remove all that confusion now itself. So there are two cases here. Depending on what is happening to the current and depending on the direction in which the current is flowing, one end will be at higher potential, the other end will be at lower potential. Let us work on this. Okay. Imagine moving. Who is moving? Some observer, or there is some probe, potential checking probe is there. Imagine moving from X to Y. If you are moving from X to Y, it means you are moving in the direction of current. In the direction of current. First case means current is increasing. Suppose current is increasing. If you are going from X to Y, you know potential at X is more than potential at Y. If current is increasing, the induced EMF will be this way. So you are going from high potential to low potential. Then the change in potential must be negative. Isn't it? You are going from X to Y. You are going from the side of high potential to the side of low potential. Okay, that high and low is created by the induced EMF. So the change in potential must be negative. Okay. It's the first case that we are talking about. Current is increasing. Current is increasing. Okay, maybe I should have written that first. Current is increasing, then di by dt will be positive. Generally, if any quantity is increasing, its derivative is positive. Okay, di by dt is positive, but the change in potential must be negative. Therefore, you can say that the change in potential is minus L di by dt. We got the formula for induced EMF as L di by dt. Di by dt is positive, but the total change in potential has to be negative. So we add that minus sign. So the change in potential when you move across the inductor is minus L di by dt if current is increasing. Consider the next case. Is this clear to all of you? Did you understand what we just found out? Okay, when you move from one end of the inductor to the other end, what happens or how much is the change in potential? We derived an expression for it. And we considered the case where current is increasing. Okay, suppose current is decreasing. If current is decreasing, we know that induced EMF will support the current and the situation will be like this. So second case, current is decreasing means di by dt is negative. But the change in potential, when you go from X to Y, you are going from lower potential to higher potential. Okay, so this time the change in potential must be positive. If you take L di by dt, current is decreasing this time, so L di by dt becomes negative. Then L di by dt also would be negative, but we want change in potential to be positive. So you have to add the minus sign once again. So basically, the change in potential across an inductor in any case, irrespective of whether current is increasing or decreasing, is always given by minus L di by dt. Okay, but when is this the change in potential? When you are going from X to Y, means you are going in the direction of current. Now, what is this going in the direction of current and all? Why will we go? We do this when we apply KVL, Kirchhoff's voltage law. We move across all the elements in the loop and we write the algebraic sum of all the potential changes equal to 0. Okay, we know how to write potential change across a battery. We'll either write it as plus E or minus E. We know how to write potential change across a resistance. If you are going in the direction of current, it is minus IR. If you are going opposite to current, it is plus IR. For a capacitance also we discussed, it is minus Q by C, where Q is charge on the first plate that you come across. Now we are discussing how to write potential change across an inductor so that we can write the KVL equation. Okay. Therefore, potential change across an inductor when moving in the same direction as current flow is minus L di by dt, irrespective of whether current is increasing or decreasing. If you are going in the direction of current, the potential change must be written minus L di by dt. In case you go opposite to the current, means you go from Y to X, then the formulas will get reversed. Then you will have an extra negative sign. Okay, so that minus will get cancelled, it will become plus L di by dt. So if moving opposite to the direction of flow of current, then the potential change should be taken as plus L di by dt. So it is very important to remember the condition and try to do this derivation once on your own. We just took an inductor, assumed current is flowing in a particular direction. One case was when the current is increasing, and the other case was the case where current is decreasing. If current is increasing, we visualized how the EMF will get induced. Based on that, we wrote the expression for change in potential when you go in the direction of current. Next, if current is decreasing, we visualized how the induced EMF will be. And based on that, we wrote an expression for the change in potential when you go in the direction of current. So in both cases, if you are going in the direction of current, irrespective of whether current is increasing or decreasing, minus L di by dt will give you the change in potential. If you are going opposite to the direction of flow of current, then it is plus L di by dt. Okay, let us apply this in one situation. We'll just write the KVL equation for a circuit. I hope you remember how to write potential changes across resistors and batteries. Okay, suppose current is flowing this way, clockwise. Resistance is R. This voltage is V. The battery voltage is V. Okay. Now to apply KVL, we choose one loop in the circuit. Now in this circuit, there's only one loop. So that loop itself you have to take. You have the choice of starting anywhere in the loop. So I want you all to start from here. And you have the choice to move clockwise along the loop or anti-clockwise. It is up to you. Okay. So I want you all to start this way and move clockwise. If you move clockwise, the first element you will come across is the inductor. You have to write the expression for change in potential across the inductor. Next element you come across as you continue moving this way. Okay. For moving also, the direction is important. As you continue moving this way, the next element you come across is the battery. You're moving across the battery in this direction. Write the potential change across the battery. Next, continue moving along the loop. The next element you come across is the resistor, and you are moving across the resistor this way. Write the potential change across the resistor. Add all three and equate it to 0. That will become the KVL equation for this loop. Okay, do this all of you. Just write KVL equation for this loop. Any answer? Okay, listen. Rishi, unmute yourself. We'll discuss.
Yes, sir.
The first thing I asked you to write is the expression for change in potential when you move across the inductor. And see, the way you
Yes,
are
sir.
moving across the inductor is already told to you. You have to go from this side to this side. If you are moving that way across the inductor, are you moving in the same direction as current flow or opposite to it?
Same direction, sir.
Same direction as current flow. When moving in the same direction as current flow, what is the formula for change in potential across an inductor? What did we derive today?
It's Li di by dt.
Write this down, all of you. There is no Li di by dt. It is minus L di by dt. Okay. If moving in the same direction as current, then the potential change across an inductor is expressed as minus L di by dt. You see, it's quite easy. L by definition is flux divided by current. So flux becomes Li. Induced EMF is derivative of flux. So you have to differentiate Li. That is how it becomes L di by dt. The minus sign, you know how we got the minus sign. Okay. Induced EMF opposes the change in current. From that, we got the minus sign. Okay, that is why I keep saying derivations are very important. Anyway, if moving in the same direction as current, the formula for potential change across an inductor is minus L di by dt. So you'll have to write the same here. Minus L di by dt. Okay. Isha, can you tell the expression for change in potential when you move from this side of the battery to this side?
So plus V.
Plus V, correct. You're going from the negative terminal to the positive terminal. So the potential increases by a value equal to its EMF. Okay. So the initial side is the low potential. The final side is high potential. When you go from low to high, the potential increases. And the EMF of the battery is given as V. So it increases by V. Okay. Next, any of you, what is the potential change across the resistor when you are going this way? Tell me, are you moving in the same direction as current through the resistor, or are you moving opposite to the current?
Same direction.
Same direction.
Same direction. Okay. How do you write potential change across a resistor when moving in the same direction as current?
Minus R.
Minus IR. Okay.
IR.
Minus IR. Okay. Let us do a quick revision of this also. Suppose current is flowing this way. Call this side as X and this side as Y. In a resistor, if current is flowing in a particular direction, it will always flow from high potential to low potential. Okay. So if you are going in the direction of current, it means you are going from X to Y. You are going from high potential to low potential. So the change in potential will be minus IR. If you are going in the opposite direction from Y to X, then you will be going from low potential to high potential. Then the change will be positive, plus IR. So if you are going in the direction of current, it is minus IR. Opposite to current, it is plus IR. Okay. So here we are going in the direction of current. So we should write minus IR. And we have returned to the starting point. So the sum of these three should be 0. Therefore, the KVL equation for this loop would be minus L di by dt plus V minus IR is equal to 0. After that, you may integrate and find out current as function of times. We'll go to that also. Okay, we'll move to that also. But basically, this is how you include an inductor in the KVL equation. So potential change across an inductor. If you are going in the direction of current, you should write minus L di by dt. If you are going opposite to the direction of current, you should write plus L di by dt. Okay. Try this question now. Suppose the inductance here is some 2 millihenry. Assume there is a resistance. Resistance you take as some 10 ohms. Let's say battery EMF is some 20 volts. Okay. At a particular instant, see, initially, had there been a switch in this circuit and the switch had been open, that current would have been 0. When you close the switch, current tends to increase, but the inductor opposes the increase of current. So current won't immediately become I is equal to E by R. It will take some time. E by R is 20 by 10, that is 2 amperes. Let's say at some instant, the current has still not become 2 amperes. It is, let's say, 1.5 amperes. Okay, so it's still in that increasing process. Okay, I want you all to find out first how much is the EMF induced across the inductor. Next, what is the rate of change of current at this moment? Try this. The current at the moment is given to you. At what rate is it increasing? And how much is the induced EMF across the inductor right now is what you have to find out. Any answer? Okay. Rishi, can you tell how you are trying to get the EMF induced?
Sir, I'm not sure about this, sir.
Okay. Isha, any idea? Fine. Listen, if you know the rate of change of current di by dt, then the induced EMF can be written as L di by dt or minus L di by dt, whatever it is, will take its magnitude. But this term is also not known. We know current, but we don't know how current is changing. So we can't proceed this way. But see, induced EMF is basically a potential difference. Keep that in mind. It's a potential difference across the inductor. And in any circuit, if you have to find out potential difference between 2 points, you can always try to apply KVL. Okay. Potential difference across the battery or potential change across the battery plus potential change across the resistor plus potential change across the inductor, should be 0. The sum of these three should be 0. This is known. Battery's EMF is given to you. You know the current, you know the resistance, means this is known. And if these two are known, can't you find out the third? You can do this, both of you. Apply KVL to find out the potential difference across the inductor. Do it carefully. And okay, let us maintain some uniformity here. To apply KVL, let's start from this corner and move clockwise. So you'll have to write potential change across inductor, which is unknown. Next, you will come across the battery, potential change across the battery, plus the next element you come across is the resistor, potential change across the resistor equal to 0. From this, you find out the potential change across inductor. Do this quickly. Yeah, one of you unmuted. If you want to give the answer, you can.
Sir, I'm not sure, but I got 1/4 into 10 to the power of minus 3.
1/4 into 10 power minus 3. Are you telling the potential difference or are you telling the di by dt value?
Di by dt value.
How much is the potential difference? From that only you will get di by dt. Or Isha, tell me, what equation did you write?
KVL equation minus 2 into 10 to the power of minus 3 into di by dt.
Okay, for the inductor,
plus 20.
Wait. For the inductor, you wrote minus L di by dt. So minus L you took as 2 into 10
Yes.
power minus 3. That is correct only. Di by dt. Plus
20.
Plus 20. You're going from negative terminal to positive terminal of the battery. So change will be positive. And resistor, you are going in the direction of current. So how do you write?
Minus 15.
Minus IR. Minus I is 1.5. Resistance is 10. 1.5 into 10 becomes 15. Okay, you wrote the KVL equation. From this, you will get di by dt. That's fine. You can directly get delta V across the inductor also. Keep this as delta VL. Okay. Plus 20 minus 15 becomes plus 5 is equal to 0. Means potential difference across the inductor or potential change when you move across the inductor is minus 5 volts. Therefore, EMF induced across the inductor is 5 volts. Okay. And then you can get di by dt value also. 2 into 10 power minus 3 di by dt. Or okay, minus 2 into 10 power minus 3 di by dt is minus 5. Minuses cancel. 5 by 2 is 2.5. Send 10 power 3 that side. Di by dt becomes 5 by 2, 2.5 into 10 power minus 3 this side goes that side and becomes 10 power plus 3 amperes per second. Is this clear to both of you? Any doubts in this?
Yes.
Rishi, did you understand?
Yes, sir. Yes.
Okay. So inductor is one of the elements of this loop. And you were asked what is the EMF induced across the inductor. So you need the potential difference across one of the elements of a loop. Whenever you need that, you can try to apply KVL. That is what worked in this case. Why were we not able to directly tell the EMF induced across the inductor? because we didn't know the rate of change of current. We knew how much current was flowing, but we didn't know the rate of change of current. Okay. Fine. Now let us try another question, this time reverse. I'll give you the rate of change of current. You have to tell how much current is flowing at that moment. I'll change these values. Let's say inductance is some 10 millihenry. Resistance is just 2 ohms this time. And the EMF is, okay, take 20 volts itself. Current is flowing this way. It is given to you that current is increasing at a rate, just a moment, let me do some calculation. Okay, 200 amperes per second. Find out how much current is flowing at the moment. Do this.
Sir, I got the answer as 1.1.
Isha, any answer?
So 9.
Let's see. Rishi, how did you solve? Like, what is the idea you used?
Sir, KVL, and then
KVL.
I
Where,
was
where,
the only thing.
Where did you start from? Which corner of the loop?
The left side, sir.
Okay, anywhere on the left is fine. Did you move clockwise,
No,
anti-clockwise?
no, downward. Like
Doesn't
down.
matter whether you start
Yeah,
from here or here, it's almost the same. Did you move clockwise or anti-clockwise?
clockwise.
Clockwise. Okay. Why I said it's the same whether you start from here or here is because there's no element present in between these two dots. So it doesn't matter where you start from. Out of these two, it doesn't matter. Okay, you said you
Yes.
moved clockwise. Okay. First element you come across is the inductor. How did you write potential change across the inductor?
10 into 10 to the 200.
Tell the formula first.
LDI by minus LDI by dt.
Minus L di by dt, because you are going in the direction of current. So minus
Yes.
L is 10 into 10 power minus 3 into
Yes,
di
sir.
by dt is 200. These are all in SI units, so you can keep them as it is. Next, you come across the battery. How do you write potential change across the battery?
Plus 20.
Okay. Potential change across battery, because you are going from negative terminal to positive terminal, will be plus 20. Continue. Next
And
element you
then,
come across is the resistance, and you are going in the direction of current through the resistance. So how do you
so
write?
it's negative minus 2i.
Minus 2i should be equal to 0. That's the KVL equation. Correct. Equation is correct. So let's see. 200 into 10 is 2000 into 10 power minus 3 is 2. So this is minus 2 plus 20 minus 2i is equal to 0. So you get 2i is equal to 18. Current is 9 amperes.
Oh, I made a calculation there.
Okay. Fine. So yeah, you seem to have gotten some hang of how to write the potential change across an inductor and what we can find out from it. Fine. So what does an inductor do in a circuit? It opposes sudden changes in current. It will allow the current to change. Eventually current will change, but it won't allow it to change suddenly. Okay. So you can write current as a function of time also. We'll discuss that. And basically, how does an inductor work? Or fundamentally what it does is it opposes the change in flux. Means it opposes the change in current. If current is increasing, the induced EMF in the inductor will oppose the current. If current is decreasing, the induced EMF in the inductor will support the current. Okay, so remember all those things, then it'll be easy to understand and visualize the situation. Okay. Now, once again, what are capacitors used for? We had recollected this in the last class also.
They store electrical energy.
They store electrical energy, correct. Okay. The two plates of a capacitor, when they are charged, equal and opposite, they have an electric field between them. In that electric field, energy will be stored. Energy stored in a capacitor, there are many formulas that you can use. Q square by 2C is one of them. You can use half CV square. You can also use QV divided by 2. Any one way you can calculate the energy stored in a capacitor. Okay. And energy density in an electric field. Energy density means energy per unit volume in an electric field. Do any of you remember the formula for this? We took help of a parallel plate capacitor to derive the energy stored per unit volume in the electric field. Okay, anyway, it is half epsilon naught E square. We take help of a parallel plate capacitor to derive this because between the plates of a parallel plate capacitor, you have a uniform electric field. So it becomes easy to derive the result, but the result is true in general. For any electric field, you can use this formula. If you know the electric field at a particular place, then the energy density in that electric field, means energy stored per unit volume in that field, is half epsilon naught E square. Now we will derive something similar for magnetic field. First thing we are going to do is derive an expression for the magnetic energy stored in an inductor. Capacitor stores electrical energy, inductor stores magnetic energy. Capacitor stores electrical energy in the electric field between the plates. Inductor stores magnetic energy in the magnetic field inside the inductor. Okay. Right. Consider an inductor like this. Assume initially there is no current. If there's no current, there's no magnetic field, there is no energy in the inductor. When I is 0, energy in the inductor is also 0. L stands for inductor. Okay. Suppose current slowly increases, then the magnetic field increases, and depending on the amount of current, there is a certain magnetic field, there is a certain energy present. Let's assume current flows this way. Okay, and let's say the current is increasing. Assume current increases from 0 initially to a final value of I. If you remember, when deriving the energy stored in a capacitor also, we first take an uncharged capacitor and we imagine charge to be transferred from one plate to the other plate gradually, step by step. Okay, and that is how we get the final energy stored in capacitor. Similarly, in an inductor, we'll assume there is no current initially and assume the current is increasing gradually from 0 to a final value of I. Or you can call final value as I naught also, just to avoid confusion. Okay. At a random instant, let's say the current through the inductor is I. Current is I and the potential change across the inductor is minus L di by dt. Okay. When current is flowing, it means, it's like charge is flowing. So when charge passes through this inductor, charge has to pass through this potential difference of L di by dt. Okay. Let's take it as delta V itself. Let's only consider the magnitude, ignore the minus sign. The potential difference is L di by dt and the charge has to flow through that potential difference. Now you all tell me, when a charge Q moves through a potential difference of delta V, what happens to its energy? Or how much change in potential energy does it undergo? We had discussed this many times. We discussed this in the chapter potential and capacitance. We discussed it in the last chapter also. Okay, before chapter. Moving charges and magnetism. When a charge is accelerated through a potential difference, how do you calculate energy of the charge? Okay. Tell me the definition of potential, electric potential. Electric potential by definition is potential energy per unit charge. So you can say the potential energy of a charge is Q into V. And the change in potential energy of a charge is Q into delta V. So basically, when a charge Q goes through a potential difference of delta V, its potential energy changes by Q delta V. It may increase, it may decrease depending on whether it is going in a favorable direction or the opposite direction. Okay. Now, when current passes through an inductor, charge has to flow through this much potential difference, L di by dt. Now, if you consider a time dt, the charge that flows through the inductor is I into dt because current by definition is dq by dt. So dq becomes I dt. That much charge flows through a potential difference of L di by dt. Okay. So we know the amount of charge, we know the potential difference. Therefore, the change in energy, small change in energy because small charge will flow in time dt. Therefore, the change in energy becomes that small charge multiplied with the potential difference through which it goes. So I dt multiplied with L di by dt. Dt gets cancelled. You will be left with Li di. Okay, that's the small change in potential energy when current I flows through an inductor. And this energy gets stored as magnetic energy in the inductor. Therefore, the total energy stored in an inductor becomes the integral of this. integral Li di when current changes from 0 to I, or I naught you can take final current. L is a constant, put it outside, integral I di. How much will that be? What is integral x dx? Or what is integral I di? Tell directly.
I square by 2.
I square by 2, correct. So this becomes L into I square by 2 as the current changes from 0 to I naught. Therefore, the final energy stored in the inductor becomes half L I naught square. If the current is I naught, it is half L I naught square. Generally, if current in the inductor is I, then energy stored in the inductor is half L I square. Simple. And for some reason, all energy formulas seem to have this same pattern. Kinetic energy half mv square. Energy stored in a capacitor half cv square. Energy stored in inductor half Li square. So it follows that pattern. That's one way of remembering it. And as the formula suggests, greater the current, greater the energy stored in the inductor. Makes sense. If current increases, the magnetic field increases. So the amount of energy stored in the field also will increase. And it is proportional to inductance also. Okay. How is it proportional to inductance? You know, inductance is flux divided by current. Okay. If inductance is high, means you are getting high amount of flux. Means the magnetic field is strong. Okay. So that will also make the energy increase. If magnetic field strength increases, energy increases. So it is proportional to inductance. It is proportional to square of current. So energy stored in an inductor half Li square. How did we derive it? We assumed there was an inductor with no current initially, no current, no energy. The current gradually increases from 0 to I. As the current increases at a random instant, let the potential difference be L di by dt. When current is flowing through an inductor, it means charge is flowing through the inductor. So it's like charge is flowing through that potential difference of L di by dt. We use that idea. When charge goes through a potential difference, charge multiplied with the potential difference is the energy gained or lost. Okay. Here, the charges will lose the energy, inductor will gain the energy. And finally, when the current becomes I, the energy in the inductor, in the magnetic field of the inductor, is half Li square. Okay. So you can also say inductor is a device used to store magnetic energy. It does that. Inductor also opposes sudden changes in current. Why? Because inductor opposes change in flux, means so it has to oppose the change in current. Okay, let's quickly go through what all we discussed today. So basically, we are continuing our discussion on inductor. Last class we discussed what is self-inductance. Now we are making use of that. Okay, any coil or a loop will have self-inductance. So any coil or a loop can be called as an inductor. So if that inductor is placed in a circuit, we discussed basically what happens. If current is increasing, the induced EMF will oppose the current. If current is decreasing, induced EMF will support the current. Based on that, we first derived the formula for potential change across an inductor. You can always write minus L di by dt if you are moving in the direction of current. We applied that in some cases of KVL. And then we started discussing, or we derived the expression for energy stored in an inductor. Okay. Little bit more is left about inductor. We need to discuss the growth and decay of current in an inductor. Okay, we'll do that in the next class. And we'll also talk about something called mutual inductance. So Thursday's class will discuss growth and decay of current in an inductor and mutual inductance. Then Saturday's class, alternating current generator, AC generator, that will be the end of the chapter. Okay, if you have any doubts, you can ask. Otherwise, I'll close this session.